In this unit, we are going to study the introduction to electroacoustics, and we'll begin by defining what acoustics is. So acoustics has something to do with sound, and actually it is considered to be science which is concerned with the production, control, transmission, reception, and effects of sound. So we are saying that it is a science which is concerned with the production of sound, how we produce sound energy, how to control it, and how do we transmit it. And if we transmit it, how do we receive it? And in addition, what are some of the effects of sound? So you can see that this area is a very wide area which can be concerned with several aspects and professions in our lives. Because you are saying any device which deals with the processing of sound, for example, the speakers, the microphones, the ear for that matter, ear, because ear actually deals with the processing of sound. It converts sound state to electrical signal and the interpretation of sound. So we all know something about sound, that whenever we are talking about sound, then it is actually has something to do with the vibrations. Vibration is created by vibration of objects. Is actually a pressure wave. So we can say that sound is a pressure wave. When we have vibrations of objects, either in air, for example, in other materials, then the mechanical vibration that results actually is what generates sound. Because you will have some particles in the space being considered. So, so we are basically dealing with the sound pressure, so that when we are dealing with how sound is produced, then we have to discuss, for example, the movement of the vibrations within the material under consideration. So acoustics can have several branches, and what we are interested in more, if it is in the electrical field, is what you call the electroacoustics. Because electroacoustics itself is a science that deals with the transformation of acoustic energy into electrical energy and vice versa. That is transformation. of electrical energy to acoustic energy, which is basically sound energy, and vice versa. But we have some other specialized branches of acoustics. Like if we just talk of, let's say, physical acoustics. Physical acoustics simply deals with the radiation and propagation of the acoustic energy. There is radiation and propagation. And propagation of acoustic energy. Other branches that we may mention, they include, for example, psychoacoustics. Psychoacoustics actually refers to the relationship between sound and the auditory events. Relationship between sound, relationship between sound sound and auditory events. Because what it means is that if there is a given sound and this sound is heard, for example, by a human being, then what is its effect? Like the music. You would find that we can use a type of music which is meant to elicit some behavior from the person hearing. Like if you have a supermarket, for example, then you would find that at certain points, maybe they play certain music. And the music that they play at any given time, studies may have shown that when the customers listen to such type of music, then they're likely to buy the products in question. So that you can see there would be a relationship between sound and the events that result when the sound has been heard. We also have up to what we call the physiological acoustics. Physiological acoustics, as the name suggests, would have something to do with the physiology, the physiology or the physiology which is concerned with the physiology has something to do with the body, the body, for example, the human body. If, for example, you hear some music, it can make you to sleep. There are some music that have soothing effects. There are some music that has healing effects. So you see, we can have a study of acoustics, which relates to the effect that it has on the physiological processes. So you can see that acoustics actually is a multidisciplinary unit, which would be important for a variety of professions, like definitely the engineers, the architects, because anytime a room is being built, then consideration must have been made on the acoustics aspect, like if it is a church, how is sound supposed to be heard? If it's a music hall, if it's let's say um, a classroom, for example, the design must be such that the intended effect on sound is achieved, maybe so that you don't have a lot of reflections. If it is a studio, for example, then there's no sound which is supposed to be reflected at all. So it would appear like a dead room, and maybe a class is not supposed to look like that. So there must be professionals that design the sound effects. So that's why we are concerned with the issues to with the room acoustics. Room acoustics. How do we design the room so that certain aspects of the acoustics, the acoustical behavior is achieved? So you would have the mechanic, of course, the electrical engineers definitely would deal with the issue to do with the room, the speakers, the microphones, but the mechanical engineers as well, because we have seen that if it has something to do with sound, it also has something to do with the noise, controlling vibrations in the industries. So you'd find the mechanical engineers come in as well. ENT, that is ear, nose, and throat doctors, would definitely be concerned with the acoustics, linguistics, people who study the languages would be part of the professors that would be interested in acoustics. Speech has a lot to do with the sound. So you can see several aspects of sound would fall into several areas of study. So acoustic is very multidisciplinary in nature, but there are certain common aspects of acoustics, especially the one that deals with the fact that we must have some vibration. We must have some vibration for the sound to be there. So understanding how the sound is generated is very key. And in our study, that is one of the approach that we are going to take. But we want to go straight into studying the origin of the sound as such. We'll first of all look at other forms of vibration. For example, for us to understand the acoustic systems, actually we need to understand so much about the mechanical systems. So we need an introductory knowledge about the mechanical systems. And if you have a background in electrical, for you to understand the mechanical systems, you need to relate it with the electrical systems. Because so many methods have been developed to analyze the electrical systems, you can use the same methods to analyze the mechanical systems. So long as we can identify the variables, the electrical variables, like the current, the voltage, the impedance. If we can relate them with the mechanical variables so that we find the equivalent of a current in a mechanical system, the equivalent of voltage in a mechanical system, and the equivalent of the impedance. And then we can relate this to the acoustic systems. So that we also get to understand the acoustic variables. How does the acoustic variables relate with the electrical variables and the mechanical variables? Because what we also would find out is that if you have an acoustic system, then it will most of the times have a mechanical system within the acoustic system, an electrical system within the acoustic system, and then the acoustic system. Because if, for example, you take a simple uh, speaker, you would have the mechanical movements involved, there are electrical variables involved, because the mechanical movement is caused by electrical. Then there's now the sound element that we convert to the electrical. You can see that there is an interplay between all these variables. So our study would actually start by discussing the vibration in general, and specifically the vibration in the mechanical systems. Then after that, we'll identify the variables that are of significance in the mechanical systems, compare them to the electrical systems, and then we'll do the same for the acoustic systems, so that we get to know exactly how, for example, does the acoustic system relate to the electrical system in terms of analogies, like current. What is the analogy of current in a mechanical system? What is the analogy of current in acoustic system? What is the analogy of voltage and impedance? Because if we do that, then we'll be able to analyze all the systems, relate them to each other, and understand them in a better way. So we'll proceed straight away and discuss an introduction to mechanical systems. So what elements make up a mechanical system? So a simple mechanical system would be made up of mass and spring. So that I have a mass, I think we have it like this. I have some spring. Then I have some mass hang on it. And this spring has some property that we call the spring constant. You can denote it by S. So if there's any disturbance, then this setup would move up and down. But if it would be oscillating, any disturbance would actually cause it to oscillate. So for a simple arrangement like this, if it oscillates, then let's say it moves up, the restoring force would be given by force equal to minus Sx, where x is the displacement. And S is the spring constant. So of course we know that you know that you can relate the F there with the equation F equal to MA. Of course, A is equal to M d squared X by dt squared. So that we have of course, here is the acceleration. So that now we can do the substitution so that we have M d squared X by dt squared is equal to the negative of S of X. Which I can actually rewrite to M d squared X by dt squared plus Sx equal to 0. Or alternatively, this expression, well, if I divide both sides by M, I will have d squared X by dt squared plus S over M X equal to 0. This is a second order differential equation, and we can solve the equation in X and get the expression in X. So the methods of solving this equation is known, and we can actually write this equation in form of in this form, so that we have d squared X by dt squared plus omega naught squared X equal to 0, where omega naught squared is equal to S over M, or omega naught is equal to S over M, the root of this. So the solution to this equation would actually be in the form of X is equal to C1, some constant, E j omega naught T, plus C2 E minus j omega naught T. This actually represents a wave. It represents a wave, because if you look at this, let's say you have the equation E jx, then it's the same as cos x plus j sin x. So this means E j omega naught T equal to cos omega naught T plus j sin omega naught T. So we are saying that there's some oscillation. This indicates some oscillation, something which changes. So that it has a maximum, sometimes it has a minimum, and then it repeats itself. If you have something that moves, maybe the X comes down, it goes up, comes down, goes up. This is how we can represent it. But there are two components here. these two components, if we interpret them, then it is like we have a wave which is moving forward with the time, and another one which is moving backward. But for now, what we can say is that omega naught is actually referred to as the fundamental frequency of oscillation. So there's no external force applied. So the system just oscillates at that frequency. So that is what, if you look at these notes that I have, is basically what we have discussed. That you have a simple harmonic motion, you just have the spring S, carrying a constant S, a mass M. Then for a simple oscillatory motion, mass M, where we have mass M tied to one end of the spring and a constant S, the restoring force can be given by this, which you have seen would eventually come to this, and then this. Or we have, as we have written this equation, then we have the fundamental frequency of oscillation. And then we have said the solution is in this form. So that is the most important aspect of this particular part. But we want to look at a little more complex mechanical system. Because what we have looked at is just a simple case where you have a mass and then you have a spring. You have a mass, you have a spring. But this one will just oscillate, and the oscillations will die out by themselves. You can bring in another element that we call a damper. Let's look at it like this. Like if you have a vehicle, then what happens is that we can consider the mass of the vehicle to be the mass, then you have the spring, so the vehicle can move up and down. But you need a damper to make the oscillations die out fast. So we can have, maybe we can have something like this. Inside here we have some fluid, so that now when it moves up and down, then this one provides some resistance. So we can call this one a damper, and it provides resistance. Maybe we can denote it by Rm, where M refers to a mechanical system. Then if we have such an arrangement, then now you have what the new equation would, the way the new equation would appear, would have I can now rewrite the equation as I can write the equation as m squared d squared d squared x by dt squared plus rm dx by dt plus sx is equal to 0. Because what we are basically saying that now in this new arrangement, you have F equal to the negative of Rm dx by dt, because the force associated with this is given by this minus Sx. Okay, and this force is given by m squared d squared, sorry, m d squared x by dt squared, so that we come up with this equation. So in this new equation, you can see we can write it as d squared x by dt squared plus Rm over m dx by dt plus s over m x is equal to 0. I can still use the same notation we had used. Omega naught is still equal to s over m. But I want to bring another variable called beta, which we are going to see it is meaning, and denoted by Rm over 2m. So that I can now rewrite this equation having beta and omega naught. Hence, we'll have du squared, so d squared x plus 2 beta dx by dt. As you can see, what we have here is that beta is equal to this, or from here you can see 2 beta is equal to Rm over m by multiplying this by 2 and by 2. So I have 2 beta there. Then plus now omega naught squared x equal to 0. So this is the new equation describing the arrangement, and this is also just a differential equation. This is a differential equation, and the way we solve the differential equations, we can always assume the solution to this equation takes a certain form. Like we know, the solution of this equation is in the form of, that is the solution is in the form of x equal to a e gamma t. If we know the solution is in this form, then we are able to bring x here. You can see I will have d squared x by dt squared. No, less we can differentiate once dx by dt equal to gamma a e gamma t, then d squared x by dt, we differentiate this again. So we get this one called down, gamma squared a e gamma t. So we can now use this to replace it here. And dx by dt, we have seen is given by this. So if I do the replacements, then I will have, for this, I will have gamma squared a e gamma t plus 2 beta gamma A E gamma T, then plus X, the value of X there, A E gamma T equal to 0. Then I can actually factorize the A E gamma T into gamma squared plus 2 beta gamma plus so there's something that which I remained here, is omega naught. Do not put it here. Do not put it in our substitution here. So that here would be omega naught squared. Then we put all this to 0. And if we divide both sides by this factor, then I have gamma squared plus 2 beta gamma plus omega naught squared equal to 0. You can always solve for this quadratic equation using the known methods. And if you do that, then you can see we'll have gamma equal to minus beta plus or minus beta squared plus omega naught squared. So that now, if we substitute this in the equation for x, then I will have, remember, we said the solution is in this form. So we can do the substitution so that we have x equal to E minus beta plus or minus beta squared minus omega naught squared, everything into T. But we can understand this a little more by looking at this equation. Let's look at this equation into a little more detail. Or this I wrote there, sorry. If we just look at this equation into a little more detail by making some substitutions, for example, let omega d be equal to omega naught squared minus beta squared, the root of this. Where in fact I can say we can still talk of omega d equal to damped frequency. Remember, we are saying omega naught is the fundamental frequency. Because the moment we do this, you can see from this expression, this one, what we have here would be negative. Because omega d is equal to omega squared minus beta squared. Okay? So this is the same as having written this one as the negative of omega naught squared minus beta squared. Then we get the root of this. So this means that if it is the negative of this, then I can now come and write omega equal to the negative of beta plus or minus j omega d, j omega d. But it is like if you, because this is the same as having this positive here or putting j squared here. So that now J squared, because you see, if you look at this, let's say we can write it as J squared into omega naught squared minus beta squared. So that the root of this gives us J into now omega D. That's how we get this J. So you can say gamma is equal to beta plus J omega D. So that if I do the substitution here, then the expression will be a bit simpler. So I will have X equal to A E minus beta plus O minus J omega D T. Or I can, if I can separate them so that I have the beta T, so I have A E minus beta T, then E plus or minus J omega D T. I just expanded this so that you can see what this means. Beta here, we cannot call it the damping factor. Because if you have, let's say, E raised to power 4T, as T increases, this value would be reducing because it is raised to the negative power. That is, if we started by here, as T increases, it would be reducing because of this negative. So the all of the amplitude would be reducing. So that is why we call beta the damping factor. Damping factor. And here we have a damped frequency. Because what this means is that if we didn't have any damping, then the oscillation would be such that we just have a constant amplitude. And the frequency of oscillation would be omega naught. But if you have a damping factor, it will start with a large amplitude, then continue reducing because of this factor, and what we have here is a damped frequency. Because you can see if, for example, beta is 0, then omega D is just equal to omega naught. So everything goes back to the undamped oscillation. Because if beta is equal to 0, here you would also just have A. This quantifies the damping. So, it is very clear that if we add a damping factor, then now you'd have your X be equal to A E minus beta T E plus omega J omega D T. We have some terms that we can define associated with this damping. All those oscillations are dying away, they are damped. So that is how we can interpret it, that you have a system in this manner. If it starts moving, it will not move forever because there is a resistance here. So the oscillations dies out at a rate which is defined by the damping factor. In electrical circuits, we have something that we call the time constant. Time constant. of an oscillation. You have a system which is oscillating, changing with time, but how fast does the change die out? Like you have a capacitor charging. What time does it take to charge fully? Or what time does it take to discharge? You have known that if you have an RC circuit, then tau, which denotes the damping, which denotes the time constant given by RC. And for an L circuit, this will be given by L over R. So you can see that we can also do the same by measuring the damping factor of this circuit. And it may have a different name, like we can call it characteristic time. Characteristic time, time constant. Relaxation time. Actually, this time is the time required to reduce the amplitude, time required to reduce the amplitude to 1 over E of its original value. Of its original value. So that if you look at this damped amplitude, this one, A E minus beta T, when would it be equal to 1 over E of its original value? There's 1 over E of 1 over E of A. When would it be reduced to this? What value of T? After what value of T would it have reduced to this? In other words, after what value of T shall it have reduced to A over E? Because the original value is A. So after what value of T? So you can see that for that one to happen, then we need this to be equal to A over E, or to be equal to this. Or we are saying it means beta T had to be equal to 1, so that we have E minus 1, or T is equal to 1 over beta. So that is what we call the time constant of this circuit. So we can say that the time constant for relaxation time, tau, is equal to A over E. Or we have E minus beta tau equal to E minus 1. Or we have tau equal to 1 over beta, which is actually equal to 2m over Rm. Because we had seen here that we had denoted our beta. We had denoted our beta by Rm over 2m. So 1 over beta would be 2m over Rm. That is what you call the relaxation time, time constant, characteristic time. Because if the value is big, then it means the system settles very fast. If it is not, then the system takes a longer time to be able to for the oscillations to die out. So this is what sometimes brings us to what we call overdamped underdamped system. Overdamped system. Then critically damped system. Critically damped system. So this part of we have discussed actually. I've discussed the damped oscillation here. That in simple motion, there is no external force applied to the system, and the amplitude oscillation will remain constant. Applying an external force will oppose the motion or the mass in simple harmonic motion. Or this is what we have discussed this. Yeah, so this the equation that we have actually derived, and then the solution will be in this form. And we have seen this, we have discussed all this, and then we have defined the relaxation time. So we can have a system which is underdamped, a system which is overdamped, and a system which is critically damped. So we can always decide, because we have said that you have a system, we have the equation. If Rm is very small, remember what Rm very small implies. Remember our beta, Vrm over our beta being Rm over 2m. So if beta is very small, then the damping factor is almost equal to 0, and this is no damping. Okay. If Rm is very small, so gamma is supposed to be equal to this. Because beta is almost equal to 0, this is the case of a undamped system. The natural frequency of the damped oscillation is this. Okay. So if beta is greater than omega naught, if beta is greater than omega naught, then it is overdamped. Overdamped because what you would have here is positive. If it is positive, then what it means is that if you look at instead of if this is positive, then you look at what is happening here. What is happening here? Then it is positive and real. It is positive and real. So the system, this value would actually be this positive and real. So it would be reducing very fast. Okay? Because this is also positive. So the amplitude will be reducing very fast. Okay, it will be dying out very fast. Then we have the case of underdown when omega naught is equal to beta, or critically down when omega naught is equal to beta. So, so up to this point, let's just summarize what we have talked about. So in this slide, we have defined what acoustics is. And we have also discussed the different branches of acoustics. But what they have in common, we have said that there is the sound energy involved, and sound is produced by vibration. So if sound is produced by vibration, then it's easy to understand the concept of vibration by looking at the mechanical systems. So we have looked at a mechanical system, a simple mechanical system that we can call the harmonic motion, which is just made up of a spring and of some constant else and a mass. And from here, we have understood the concept of the fundamental frequency, that the free oscillation, where the frequency oscillation is just given by this. But we can have a damped system by you bringing a damper so that the oscillations are forced to die out. And if we do this, then we'll come up with a modified system. And if you have the modified system, then now we'll be interested in measuring the extent of damping in using what you call the damping factor. And we have derived the new equation, and we have seen that we'll have a system would be either be underdamped when beta is very small, of a damped, and beta is greater than omega naught, and critically damped. Critically damped when beta is equal to, when beta is equal to omega naught. Okay, because we are referring to this equation that we have here. The equation here to determine the extent of the damping. So in our next lesson, we are going to look at the case whereby we are applying some force. Because most of the times you are not just going to have you are spraying there, then the mass, then it is just oscillating, or with a damper, will have to be applying maybe some force. That's what we model most of the system. You apply some force. Then we'll discuss this, and then we'll see how to relate this with the electrical systems. So let's meet then.